Greetings. I am Rishita Umashankaran from BMS College of Engineering, and this is my submission for the competition Ascension, which is a 36-hour data science hackathon. Before I begin, I would like to thank BMS CIEEE Student Branch and Altair for giving us this wonderful opportunity in exploring machine learning and the very creative tool that is RapidMiner. So coming to the topic that I have chosen is sustainable urban living. Basically, we're checking the properties habitability using machine learning and the RapidMiner tool. Let's get started. So coming to some of the contents of this report, I would like to start with going the brief overview before we go to the demonstration of the model itself. So coming to the problem statement, finding a suitable place to live is a crucial decision that significantly impacts one's well-being. While online listings provide some information, it can be challenging to assess a property's true habitability based solely on descriptions. So this basically judges how sustainable and habitable a property is. Moving on, the dataset that I've used is an ML Olympiad Sustainable Urban Living dataset from Kaggle. This basically includes a variety of features essential for evaluating urban spaces living habitability. And this has been the location that properties have taken from is based from US. Some of the features that are included in this dataset are property ID, property type, property area, number of windows, doors, type of furnishing, frequency of power cuts, power backup, water supply, traffic density score, crime rate, dust and noise, air quality index, neighborhood review, and finally the target label, which is habitability score. So some of these attributes are numerical, some of these are categorical, so we'll be processing them in different ways. Moving ahead, the simple methodology followed in our project is first we're doing a dataset selection. In this case, we've chosen property details, the urban living dataset, then pre-processing, then we'll be training the model, and then we'll be doing predictions on the model. This is a general overview of our methodology. Moving to the details, again about the dataset selection, we have thoroughly analyzed different datasets already available on Kaggle, and I found this thing to be more relevant in today's society, where we're moving towards sustainability, and finding whether houses are contributing to that is a very important decision to make. And using AI to do that is a very great thing, in my opinion. In data pre-processing, I've done two major things, that is handling missing values, and I've imputed them using the statistical measure that is mean, ensuring data integrity and completeness. Next is feature engineering, and the thing that with the increased number of features is that it makes our model very complex and it might take more computation time as well. So decrease that, I've combined the number of windows and number of doors to create a new feature called total openings. This has been tested and I have noticed that it reduced the root mean square error by 0.1, and that is a very significant difference. Next is the model training. So the model that I've chosen for this dataset is RandforestRegressor. So this ensemble learning method builds multiple decision trees during training and aggregates these predictions to improve accuracy and reduce overfitting. And I've also used cross-validation techniques as it is used to validate the model's performance, and it ensures it generalizes well to new and unseen data. Then we are doing the predictions and testing them on the different performance measures, mainly the root mean squared error RMSE and squared correlation coefficient. So RMSE is very familiar, but something new is that squared correlation coefficient. This assesses the linear relationship between predicted and actual habitability scores, indicating the model's explanatory power. Moving on, the model evaluation, as mentioned before, we have gotten a result of 7.011 with a plus or minus variance of 0.3507. And we have a scored correlation of 0.768 with a plus or minus difference of 0.0480. So this is a very good score that I have got through my random regressor model, and I'm proud to document the same. Coming to visualizing the predicted versus expected values, as we can see in this plot here that I've generated on the RapidMiner tool, the blue values are the habitability score that is given in the dataset already. As you can see, the green values are the predictions that are made by my model. There is a very less variance in this model, as almost all the values in the median range are accurate, and the outliers such as the bottommost values around the 20 range are not correctly evaluated. So my model does a very good job at predicting the results. So coming to a little about the RapidMiner tool, I found it very easy to use because of the drag and drop interface and the descriptions that each tool gives you. It helps you to identify errors because it's a new thing that there's a difference between coding machine learning and implementing it. So I found these little snippets and information about each tool, how to use it, very useful. And definitely the visualization tools, I do not need a new, say, code to write the visualizations. I can plot any number of plots I want with already available variables in a very seamless manner. And RapidMiner, I believe, also supports seamless deployment of these predictable models. So we can also apply it to different areas of life and ensure that it's utilized in the real world as well. And definitely the quality of experience and the computation power of this tool is really commendable. Coming to the acknowledgements, again, I would like to thank Altair and BMSC IEEE for organizing this. In conclusion, this project has not only enhanced my skills in data science and machine learning, but also highlighted the importance of leveraging technology to promote sustainable and livable urban environments. Now that I have gone through the project in brief, I would now like to do the demonstration of the project on the tool. Thank you. Hello everyone. Now coming to the demonstration part of the model. So here we are loading the data set from the local repository, which is named under data and urban. This is what we've loaded over here by dragging and dropping it. The original data has around 31,000 rows. So we're using stratified sample to extract around 5,000 values and use that sample data to train our model. As 31,000 rows is a lot of data, processing time increases a lot, and we don't want to spend too much time on that, as the motive is to train the model and evaluate the performances in general. So 31,000 is not necessary in this context. So we've used split data for that, and we've taken the 0.2% of the data and trained that. Coming to the next part of it, which is the pre-processing. Here we're doing two major things, that is handling missing values by replacing it with the mean of the remaining values, and something called as feature engineering, where we're creating new features, new and meaningful features from already existing features. Two things that it achieves is that it you create data that is more meaningful and gives better outputs on predictions, and you're dropping unnecessary features. So that also decreases the complexity of the model and improves its overall performance. So we're using replace missing values and replacing it by average. So that's how we're filling the missing values. Generate attributes is basically for creating the attributes like this thing, the feature engineering, where we're naming a new thing called total openings by adding number of doors plus number of windows. Cool. Then select attributes is basically to select all the new attributes that is just generated. And we are excluding the the subset of attributes, which is the number of doors and number of windows. This won't be necessary. So we're removing that from the data set. Next, by setting a role, basically we have to mention which is the target role. Here habitability score is the target label, hence that is mentioned here so that model can recognize that and accordingly do the computation. So that concludes our pre-processing of the data. Moving on to the training, we have used cross-validation to conduct the model training. Let's look into that in detail. And the model that we've chosen is a random forest, which is basically an ensemble of decision trees. So coming to this, we've used model training we've used a number of trees is 1,000. The criterion is least square because we're using numerical data and it's a regression tree, not a classification tree. So we need to use least square method, and the tree maximum depth we've given is 10. So this is our random forest ensemble model. We're using the apply model concept here to make the predictions. The predictions are then inputted into the performance task, where it's evaluated using the root mean square error and square relation. These are other performance measures as well, but we'll be focusing on these two for now. So this is what happens inside the cross validation. It basically creates a number of folds, which I will show here. So it creates 10 number of folds. What basically happens, it splits the data into a couple of folds. It trains it on some of the folds, and the remaining data is then tested on unseen data. So that's the concept of cross validation, where we're improving it in such a way that it can make accurate predictions even on unseen data. So that covers our model structure. We can see it in overview as well. So this is how it looks like in the bigger picture. We are sampling the data. We're extracting only a good number of features for our model. Pre-processing is done here. And here we're doing the training and evaluation of the model. So coming to the results, let's look into some result that has already been generated. Alright, so we've just executed the model. let's check out the example set. So here we can see the data. This is the habitability score that is already present in the data, and this is the predicted score. You can see that it does an almost accurate prediction of the values. Here it's 93, 90, 73, 74, 80, 81.9, 69, 80. And in a few values, it is not completely accurate, but overall, it does a very good value of predicting it. Let's do a simple visualization to see how this works. Yeah, so here we can see, let's first see just the habitability score. So here we can see this is the original data, and here is the prediction. Now let's see how they compare together. So here's the habitability score, prediction score. We can see that it's almost overlapping in all the places, except for a couple of outliers and some values on the top. So this gives a good visualization of how our performance has been done. And you can also see how the data has been, how many values you can see here. This is the frequency, some of them are numerical values and some of them are categorical values. And here we can also see the total opening values that we created. So these are the different features that are existing. Coming to the performance, here we can see the root mean square error as 6.7. Before I did the total openings, that is the feature engineering, the performance measure was around 7.8. So you can see that there's a huge difference when we are do feature engineering tasks, and that can create a more well designed and better performing model as well. Squared correlation is 0.77 as mentioned in the report as well. So as we can see, our model does a very good job in predicting the habitability score of the properties in USA. Thank you.